you like memory, what it is like, that's what, you know what I mean? Yeah. So you know what RAM is? Yeah. Okay, so RAM is like all time, RAM is all time. Yeah. Yeah, yeah. They do it and it's gone. Well, like RAM, like holds like processes things, so like you're, I don't know, so, like doing something, right? And then like you have like SSD or you have like storage, like an actual storage, like HDD or whatever. That's non-volatile. So on there, if we access the RAM memory, when you turn on your computer, that RAM memory gets like it's well, that's what the volatile. So like if I turn on my computer right now and I open up my files, I'll still have this JU or this screenshot. But if I had like something stored in RAM and I can close my line up, it'll be gone.
Yeah, I think it's like if it gets any command at all, it might override it essentially, even if you're not like directly telling it to. So that's why I think after you call it, you want to move it out again before you do anything else.
Basically, just keep it non-volatile.
Yeah. Because you don't know if it'll interact with it or not.
Okay, everybody, let's get underway. Today is this one here. No, it's great to have six, no, I don't know how many, 5 SI meetings per week, but I can't remember them all. So at the beginning of lectures, I used to write them all down, but you're going to have to just look for them. Visit Discord for 3 minutes and check and see if something's been posted, like an announcement, and then you'll know when they meet. Okay, enough said. Last lecture was about 2's complement integers, but today we move to float numbers. That's this right here. Okay, and the goal is that you be able to translate decimal floats to IEEE floats and backwards, forward and backwards conversions. Okay, so to get started, it's here. Okay, so we have to, the background is, think of decimal floats in exponential scientific format. So they look like what, 375.946 times 10 to the 7. That's exponential format, but it's not scientific. And so to make it scientific, I need to change paper here. That's it. Okay. The blue ink's not important. The lecture starts with the black ink. This one is exponential format, but it's not scientific. To be scientific, you can only have one non-zero digit on the left of the dot. So 3.7596 times 10 to the 9 meets both criteria. It's scientific and it's exponential format, both. Okay, so notice that the digit over here is a single digit and it cannot be 0. Single digit, not 0. And the base number is fixed. If you're in ordinary decimal numbers, this is fixed at 10. So just say the base number. Okay, so our goal is, what we're driving for is to get a float number represented in binary digits, scientific exponential form. Scientific exponential binary float number. Okay, in binary, there's only 2 digits. Only 2 digits. And the rule is that the digit on the left side of the dot cannot be 0. So you're forced to the conclusion that only 1 is allowed on the left side, and that's true. 1.01. 0.001 times 226. Okay. There's an example of what our goal is to make it look like that. That's a 6. There's an exponent up there. Some you can overdo it sometimes. Some students have complained that that isn't right, that I should really write 2 as 10 and 6 as 110. But so what? You know what it means. It's 2 to the 6, no matter how you think about it. Okay, and so this part is 0.111010001 is generally called mantissa. And this one up here is true exponent. We're going to get another exponent that's not the true one. So it needs the adjective true in front of it. That's the true exponent. And the base number is here. I think you can see that. Thanks. All right, so let's attempt this. We're going to start with a decimal float number and convert it to IEEE form. So begin. How about 33 point, what's a good one? 375. Okay, we'll try that. 375. That's our starting number. It has a integer part and a fraction part. So we use techniques from last class meeting to convert 33 to binary. Okay. You can divide by 2, but for small numbers, it really isn't necessary. You look at that and say, oh, that's too close to 32. Okay. It's too close to 32. Okay, you say, look at that. What's the highest power of 2 that's less than or equal to that? It's 2 to the 5, which is 32, minus 32. My example is ruined because there's all zeros coming now. So then you say, what's the highest power of that? That was 2 to the 5. 2 to the 4 is 16. Is 16 less than or equal to 1? No. The next power below that is 8. Is 8 less than or equal to 1? No. Is 4 less than or equal to 1? No. Is 2 less than or equal to 1? No. Is 1 less than or equal to 1? Yes. There's the binary number for 33. 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5. 2 to the 5 is 32. So there's 132 and 1 1. I guess we'll continue with that again, but it's kind of non-common. Too many zeros in there. Okay, then we take the 375, the fraction part. The formal algorithm for computing the binary representation of a whole number is repeated division by 2. The standard algorithm for converting a fractional part of a number to binary is repeated multiplication by 2. So here we go, by 2's. 5 is 0, 1 to carry 14, 15, 1 to carry 6, 7, point, look this over here. I think I did that right. Okay, then you repeat it, 75 times 2, 0, 14, 15.1, and then you repeat it. 0.5, I'm going to drop the 0, 0.5 times 2, 1.0. And when you reach to the point where this is 0, you're done. Any further multiplications by 2 just gives you more zeros. See, so there's no point in it. Okay, so we can stop here. When you convert an integer like 33 to a binary number by repeated division, you read your answer off backwards. But when you convert the fractional part to binary by repeated multiplication, you read your answer in forward direction. So it would be, let me use a different color. It would be here, here, and here. What we get out of all that is that 3.375 equals 0, 1, 1 dot. Okay, so now we have 2 halves, we put them back together. The first half was on the other page. 1, 0, 0, 0, 1. 1, 0, 0, 0, 0, 1, 0, 1, 1. That's our floating point number converted to binary, but it's not IEEE yet. Nice number, but it's not IEEE form. To get to IEEE, we have to make it scientific. So scientific can have only 1 digit on the left side of the dot. Here we have a bunch of digits. So this dot gets transferred to here. And then it reads as 1.0000101 times 1, 2, 3, 4, 5, 2 to the 5. Okay. Now that's scientific. It has a leading single digit on the left side. That single digit is not a 0. It's multiplied by an exponential term using the base value. We're in base 2 now. And it all looks good. This is a scientific exponential binary float number. No, all those words. Okay. So this is called mantissa. And this 5 is called true exponent. The 2 is just called base number. And the poor 1 over here is called, it's discarded. It's called hidden bit. Watch in a few minutes, you'll see we throw it away as being not important. Okay. Let's see what we have to digress for a moment. In the register, this exponent is going to be transformed to another exponent called stored exponent. The stored exponent is allowed to use 11 bits. So the machine doesn't store 5 directly. It stores this transformed exponent. So numbers in 11 bits, integers in 11 bits, range from 0 to 1, which happens to be 2047. Now, what's of interest is the number exactly in the middle. We want to know that number. Midway between 0 and 247. Well, okay. Here, let's cheat and go in the back door. Halfway between is 2, 0, 47, and 23, 2, 46, and a remainder 1. Okay. But the question is, what is that in binary? 1023. Is the middle number, it's actually 1023.5, but we can't work with fractional parts here. We round down to the nearest integer, which is 1023. And by the way, that's so important, that actually receives a name. Its name is bias number. Okay, and it's fixed for all 64-bit floats. Later in the semester, we'll do 32-bit floats. They have a different bias number, but for us, this is king. Okay. Now, if in case you're wondering, what is it in binary? 1023 is a single 0 and 10 ones. Okay. Once. Okay, we go back to our problem. Our problem left off right here. We can't use 5 as the exponent. The exponent we use is the bias number plus 5. So we have to compute 0, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, plus 1, 0, 1. Little Indian style. Okay, and you remember from yesterday, 1 plus 1 is 10. 1 plus 1 plus 1 is 11. Okay, we have to use it. I think we use that here. I'm not even sure. Okay, let's add. 1 and 1 is 10, carry 1. 1 and 1 and 0 is 10, carry 1. 3 ones in a row is 11, carry 1. 1 and 1 is 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 1. So that is called stored exponent. Stored exponent. Stored because it goes into the computer. The 5 doesn't, but this one does. Okay, we adopt the convention that a 0 bit means positive, and a 1 bit means the number is negative. That's easy to remember. Now we throw all the pieces together. Ready for this? Okay. Okay, the number we started with was 33.375. There it is. 0 because it's positive. Why do we care? I can't tell. Oh. 0. Then the stored exponent. Then it keeps going. And it keeps going. And then you look back at your scientific form, which is here, and you copy that into the register. It just looks like 4 zeros and then some other data. Okay. Now, I've run out of digits because the mantissa is only 8 bits, but there's lots of trailing zeros that are not written. So at the end of this, I have to have enough zeros to fill out 64. There's a lot of zeros at the end of this number because it's not a repeating number of any kind. It's very 375. 0.375 is very finite. In fact, it's 3/8, I think. Okay, that's the IEEE floating point number representing what was our number again? It was 33.375. See if I can put it here. The whole thing. Okay, so that's what's stored in a register of 64 bits. And for the side information, for your information, this is least significant. No, I said that wrong. Or no, I did say it right. Least significant byte. And this is most significant, MSB. Okay, so binary is very hard for humans to deal with. We like to read hex numbers. And so the last step of this process is to put it into hex. That red ink up there. Well, you look at it. I've already put in groups of 4. The first one is an 4. The second group is 0. The next group is 4. And I think 404 means dead web page. And then there's a 0. And then there is 11, which is B. And then there's all these zeros again. Oh gosh. To complete the answer, you need 16 digits. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. There it is. Okay, that's what you'd use in your program, probably not all those binary bits. If you needed that number, it's a float number, moved into a register, what do you do? Well, I think I put that in a register first. register wants all 64 bits. You have to count this all out again. That's 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Push it. Copy it. Let's name something here. XMM8 topic stack and pop. Now XMM8 holds 33.375. And the number placed in XMM registers, it doesn't work if you don't do it. They're all IEEE 754 numbers. All floats in XMMs. IEE 754 numbers. IEEE, I don't know, a long time ago, set this standard that you're seeing right now, and it's in one of their documents, number 754. So if you really wanted to see the original definition, you can go to their server, and I'm pretty sure you can still read this document. Nobody does. But that's become the standard for float numbers in computers. Okay. Any questions?
Could you explain the part where you have like 0.375 x2? Could you explain how you're doing that?
Yes.
It's just
right.
You're just multiplying it up
Okay.
from the left there.
It came from back here. So 33 was dot dot dot. So the 33 is here, and the 375 is over here. Mm-hmm. So that's a floating point binary number, but it's not scientific. So the arrow says slide your dot over here, and then it looks like, am I under the camera? It looks like one dot, all those zeros, they stay there. But the number of places that the dot moved is recorded up here in an exponent. Technically, this is times 2 to the 0, which doesn't do anything. But when you move the dot to the left, then the exponent on 2 increases by that many places. And so this one now is finally binary scientific floating point number. But it's not right. It's not yet IEEE. That's another step to go. Okay. But this is an intermediate stage between, here's the starting point, way back here. It's an intermediate stage between base 10, scientific exponential number. You get to a base 2 scientific exponential number. Then there's 3 parts here. There's the 0 for positive. There's this 5 to deal with, and the mantissa part to deal with. And we lay them out in that order: sign bit, stored exponent, and mantissa. That's sort of, here's the register. This is the sign. This is the stored exponent. And the rest of this is mantissa. Okay, so this is 1 bit, 11 bits, and it's 52 bits for the mantissa. Sometimes you have a short mantissa like ours here. It's only 8 bits, but the rest of the register is filled with trailing zeros. We end up here 0, 0, 0, 0, 0, 1, 0, 1, 1. Then all this space out here, nature can't have a vacuum. It has to have something. So it's trailing zeros until you have 52 total in the mantissa section. That's an XMM register. Any one of them looks like that. Okay, and where did I go with this? So I think I'm not in charge, but I think the excuse me, the SI leaders will lead you through the development of IEEE numbers, starting with base 10 float numbers. Let's try a hard one for practice. Okay. Let's go with 85.1. You say that doesn't look hard, but it might be. Okay. Let's go. You separate it in whole number part and fractional number part. Okay, the whole number part, 85. How can you do that and save time? You count in multiples of 2. 4, 8, 16, 32, 64, 128. So this is not as large as 128. We have to stop at 64. So there's 164 here. Subtract it away, and it's 21. Then in what's the largest power of 2 less than or equal to 21? We know it's 16, but we skip over 32 in the middle. And we come to 16. Yes, 16 is less than or equal to that, so you record it, subtract 16. The next power of 2 is 8. It's too big. You record it as 0. The next power of 2 is 4. Yes, that's good. Which is a 1. The next power of 2 is 2. That's too big, so it doesn't appear. You go to the next one. The power of 2 is 1. That's good for us. And it's a 1. And when you reach 0, you stop. Okay. So there's 85. Okay. Now, if the integer you're working with is 3,729, this technique kind of doesn't work. It just, you got to go to divide by 2s. But for small integers, less than 500, you usually do this. Okay, so the next part of the equation is 0.1. When you convert a fraction, you multiply by 2, not divide by 2. So we do this. And then I'm going to go across the page. 0.2 times 2. And I'm kind of pausing here because you look back where you've been and you see you're repeating yourself. This block is starting to repeat itself. So it's a repeating binary fraction. So the bits, when you're doing the repeated division, you read the answer off in backwards order. But when you're doing the fractional part, you take it in forward order. So it's a little underline where it's coming from in that order. It says that 0.1 decimal is equal to 0.0011001100 amount of space, dot, dot, dot. Keeps, the pattern keeps going. 2 ones and 2 zeros, 2 ones, 2 zeros, 2 ones, 2 zeros. Okay, so now we can write our number in binary scientific. Oh, no, it's not quite scientific. Okay, it's binary floating point expression. Okay, so number M, I spell BER equals 1010101 dot 00011001000 times 2 to the 0. There's the expression. But it's not scientific because left side of the dot can only have one digit. And so we need to translate this to here. That's 1, 2, 3, 4, 5, 6 places. Then it reads 1.0101101. That's the 6 places, and then the rest of the mantissa continues. 00010. Dot, 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 times 2 to the 6. Looks like that. Okay. Scratch paper. Let's work on the 6. On scratch paper, we need to add that to the bias number. 0, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 0, 0. Okay. There's lots of space for huge exponents. What if the exponent was 100? There's enough space to fit it in here. If the exponent is greater than whatever it is, 1024, you're running out of space. Okay. So let's add 1, 1, 10, 1, 10, carry, 10, carry it, 0, 10, carry it, 1, carry it, 1, carry it, 1, carry it, 1. Okay. Why does it look strange? 6. You know, I have a mistake. I added 4. I have to add 6. Okay. The bug is here. For accuracy, let's do it again. 0, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 0. And 1, 10, 1. There's 1 plus 1 plus 1, which is 11. We record 1 and carry 1. That's those two add to 10. That's 10. That's 10. That's 10. That's 10. That's 10. 10. That looks correct. So if you play back this on recording, that doesn't count. Okay, that is stored exponent. I think we're ready to put the pieces together. So the sign is 0 because the number was positive. Then you copy the stored exponent. And then we go back and pick up the mantissa, which is, it's that right there, starting at the dot, and the poor one on the left gets thrown away. So I'm going to run out of space, I think, but let's 0, 1, 0, 1. We're up to here. 0, 1, 0, 0. We're up to here. 0, 1, 1, 0. We're up to here. 0, 1, 1, 0. And we're here. 0, 1, 1, 0. 0, 1, 1, 0. Dot, dot, dot. 0, 1, 1, 0. Okay. Enough. Yeah, repeat that quadruple enough times so that there's a total of 64 bits. Okay, that's what the computer likes. That's what it actually has in XML registers. But for us humans, we need something we can read. So by habit, I already put them in separation by groups of 4. You see the little blank spaces. So the first one is a 4. The next one is a 0. The next one is a 5. The next one is a 5 again. How's that happen? The next one is a 4. The next one is a 6. 6, 6, 6, 6, 6. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. That will be, that's it. Mm, wow. Program like this. Give it a fast car and see if I can locate it. I don't know. Yeah. Wow. Okay, let's share a screen with you and see what this does. We'll use the same data and see how it stacks up. Um, where is- Okay. There it is. Okay. And we need to activate, give permission. CHMOD user receives execution privileges on the file run in SH. Okay. Yeah. I did some, I spelled that wrong. Okay. CH. That's embarrassing. Okay, I gotta spell change mod correctly. CHMOD. I better be okay. And then okay, run is in green now. So /run .sh. I still can't spell it. R U. Oh,
You're missing the slash.
oh, yes, thank you. RUN.sh. Okay, it says enter a floating point number using decimal digits. What's the one we last had here? It was the last number we had 85.1. Okay, 85.1. 85.1. Okay. So the answer we're concerned about is this one. Look at all those sixes. And you can't see it, but the piece of paper says 405546666666. And we did it right. That's it. Machine generated. And next to it, oh, okay. So here's something you should know about. The computer can't show every floating point number on Earth. It can only show a finite number of them. Math course will tell you there's infinitely many floating point numbers. So I wanted 85.1. What you get is the closest value to 85.1 that the computer knows about. And it happens to be that one over there. This is not unusual. It happens all the time. The nearest number that the machine knows to the number I wanted is 85.0999999, and eventually it even loses the 9 at a 4. That can't be helped, but it's something you should be aware of, that there are many float numbers that can't be expressed precisely in any computer. Okay. Later in the semester, we'll look at float numbers in 32 bits. And this is what it looks like. It's half as many hex digits. And the precision is even less. This is type float in a C++ program. The precision over here, notice, starts to fail after about 4 digits, 5 digits in the fractional part. Here it starts to fail after many more, I don't know, 8 or 12 digits. One more. What was the first number we did? It was
33.375.
Oh, yes. Let's try now. 33.375. This is finite. This is binary. It'll give you a precise, accurate answer. 33.375. And the machine says this one here. 404. And somewhere back here, I got the calculator. Where did I put it? Yeah, okay. Paper says 4040B and then all zeros. And the machine up here says 4040B and all zeros. And that one's precise because there's no round off factor to the nearest number that can hold 33.375. It can hold 33.75 exactly. Okay. So what's our clock say? It's 10 minutes before the 11 o'clock. The other half of this equation is sometimes your midterm asks you to go in reverse order. Start with the IEEE number, come up with the decimal number. Let me, before we go that direction, let me point out that the nice numbers, whatever nice means, nice numbers, are those around 1.0 decimal. Okay. Numbers that are astronomical in size, they're quadrillion digits involved. Those are not nice. They're not. So around 1.0, you get really nice looking numbers. 0x401 08000. Okay. And they're all there. You'll notice that the stored exponent in here will be close to 400. It might be one below that is by the way, is 3FF. 400, 401. Okay. I think 3FF with all zeros is 1.0. The last 10 minutes, let's do that one. Okay. So we start with 1, just 1.0. This is real easy. Okay, we want to convert it to binary form. It's 1.0000 times 2 to the 0. Stored exponent. Base number. Mantissa. Throwaway. Okay. The stored exponent is 0. We have to take the bias number 0, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, and add 0. You don't get anything new. This is now the true, I wrote that backwards. That's true. Now this is stored. Stored exponent. Okay, I think and there's the mantissa. We're ready to write the number. Here it is. It's positive. 1.0 is positive. Its stored exponent is that one. Its mantissa is lots of zeros. Let's go hex with it. That's a 3. That's an F. That's an F. And everything after that is zero. Zero. So a clean writing would be, I can't see my own camera. Oh, I gotta stop the share. Where'd it go? I can't find it. Lost. Where'd it go? Oh, okay, I think I can find it. Okay, let me slow down. I didn't. There's an oversight. I missed turning the camera back on. Okay, we're starting with the number 1.0. Okay. And here it is. Start with 1.0. Okay. Write it out. It's 1.000 times 2 to the 0. That's the true exponent 0. So the algorithm says add your true exponent to the bias number. Bias. This is true. Add them together, but adding 0, nothing changes. So the stored exponent is the bias number, just by the sheer special case of 1. Then you're ready to write this number. The first digit is the sign, 0. Then comes the bias number, which is the stored exponent. Then come all zeros, because the mantissa up here is all zeros. Okay, so I started to convert it to hex, and we'll make it a clean hex here. It's 0x 3f f 0 0 0 0 0 0 0 0 0 0 0 0 0. That's 1.0 in decimal. Yes, Seymour. I can't write it. Okay. So 3FF, that's the stored exponent showing up there. 3FF is 1 digit away from 400. I was telling you a few minutes ago, the nice numbers are close to 400. Okay. We won't do we're running out of time, so we won't do the math, but that happens to be 2.0 in decimal. Okay. Let's add a digit 1. 4, 0, 1. You add 1 to the exponent. This doubles over here. This happens to be 4.0. Okay. The nice numbers are close to 400 or 1 less than 400. I'll go 1 more. 402, all zeros. That'll be 8.4. Okay. Now, you want to play this game. 8.0, what did I say? Sorry. 8.0. So 3 is halfway between 2 and 4. What do you think is halfway between here and here? Well, see, if you wrote it out in full, just this first part and this first part, that's 4, 0, 1, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. And then the next one below that is, that's, oh yeah, it's 4. Where's the 1 come in? Yeah, 0, 0, 0, 0, 0, 0. 1. That's those two numbers. Make them stand out. There they are written out in detail. Halfway between would be 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1. It's got a 0 and 0. So a 1 in fraction is a half of something. Just 0.5 in decimal is a half. But that's 0.1 in binary. Half of that is 0.25, or 1/4 is half of that, 0.01. That's how you take the half of a binary fraction. Okay. 0.75 is 3/4 is we need to add a half. Okay, so that's what I'm doing here. The number in between, it has this as its starting expression, and that's a 3.0. I'll conclude with this. So I'm going to take this first one, and I'll just repeat it. 0, 0, 0. 1, 2, 3, 4. 1, 2, 3, 4. 1, 0, 0. And so on, all zeros to the very end. That is a 4, a 0, a 0, an 8, a 0, 0, 0 to the very end. In other words, 3.0 is 0x 400 and halfway more. 8 starts with a 1, 0, 0, 0. That's adding a half. Okay. See if that's still there. Yeah, I close. Okay. Let's go once more. Now I'm going to end here. Okay, what did we want? We wanted 3.0. 0. And see how you add a half. 3.0 is halfway between 2.0 and 4.0, and it results in this 8 in there. The 8 got in there because its first digit is 1. 8 is 1, 0, 0, 0. And that 1 makes a half more. So it's confirmation that the mathematical theory is all correct. There's 3.0, and here it tells us, yes, you're looking at 3.0, and it's 408. Okay, so, oh, I forgot it again. Oh, am I sharing this screen? Stupid. There it was. I entered 3 back here. I entered 3. And then it says, in IEEE, it's 408. The 8 has the property that it's a 1 followed by 0. That added the 1, which got us halfway between 2 and a 4. Nah, we're done. I'll leave these little techniques for another day. Okay, so you can count through powers of 2. 1.0 is 3FF. 2.0, you add 1 to that, and it's 400. 4.0, you add 1 to that, and it's 401. 8.0 is 402. And you know what 16.0 will be? 403. And you could have a mantissa stuff here, but precisely 16.0 will be this number with all zeros following it. All right, clock says 11:06. We're done. Have a great day. You're going to be programming, and then my job is this weekend to make assignment 2 and post it. Check back once in a while and see if I get it posted. Class is over.
Okay.